Okay, it's 11 o'clock. Let's get started here. So today we will continue in Chapter 6. After today you'll be able to do most of project number 3, I think, depending upon how far we get. Project number 3 is due on Wednesday, October 24th. And of course we do not have class next Tuesday due to fall break. Are there any questions before we get going here? Okay, let's start these 6.5 to 6.9 notes. What we've been talking about in Chapter 6 is how we can do multiple regression analysis, meaning that we have more than one predictor variable now in our model. And a lot of this stuff is just simple, basic extensions to what we have been doing previously. Also, we're talking about everything in the context of matrices, which allows us to basically apply the exact same stuff from Chapter 5 now to Chapter 6 with just slightly different definitions of what the X matrix looks like. So, for example here, we can talk about a covariance matrix for B. So these B's, again, are our parameter estimates. Parameter estimators, I should say. They are statistics, so they vary from one sample to another. We want to be able to quantify their variability by looking at variances, and then also the relationships amongst each other using covariances. So the covariance matrix for B, and again, B would be of the following form. It's a vector that has the form of B0, B1, down to, and I'm running out of room, so I'll just come over here, down to B sub P minus 1. If we think of these B's again as statistics that are random variables, then this is the form of the covariance matrix, just the same form that we saw in Chapter 5. The only difference now is that this matrix is bigger. This matrix specifically is P by P in dimension. Again, on the diagonal of the matrix, this is where we have the variances. On the off diagonal, we have covariances that measures dependence. And just like in Chapter 5, then, the actual covariance matrix itself has a nice compact form when we put everything in terms of matrices. It's sigma squared times x prime x inverse. That's it. The estimated covariance matrix for B, then, notice how I'm putting a hat on the various elements, is just simply the mean square error times x prime x inverse. So all I did was I replaced sigma squared with its estimate. Note that you can, with this notation here, you can get a little bit in trouble in terms of, I guess, the notation itself, because, don't think that I'm taking the matrix M times the matrix S times the matrix E here. This is MSE. Sometimes other books, and I prefer this notation, would actually simply denote the MSE by sigma hat squared. But this is what we do. Now, once we have this covariance matrix, then often these variances are very important to us because we can use these variances then in a hypothesis test to help us determine if a particular parameter like beta sub k is equal to 0 or not. So you hopefully will remember us doing Ttest back in Chapter 2, where we tested is beta 1 equal to 0 or not. Well, now we can just do it for any beta of interest, and this is what the Ttest would look like. So this is our model written in general. Let's say that I'm interested in x sub k. Is x sub k, given all the other stuff that's in the model in terms of the predictor variables, is x sub k really worthwhile to have in the model or not? How do you make that judgment? Well, if beta sub k was equal to 0, notice what would happen. X sub k would disappear from the model, and you still have everything else in there. If beta k does not equal 0, well then, of course, you do have x sub k in there. So this is how we state our hypotheses then, as you might expect. Our test statistic, exactly the same as what we had in Chapter 2, except for now we have a little k here to say which B and beta we're talking about. Again, we denote the test statistic as T star. It's a two-sided test, so the critical value is going to be a plus or minus 1 minus alpha divided by 2 quantile from a t-distribution. Here's one change from Chapter 2. Notice the degrees of freedom here is n minus p. In Chapter 2, we had n minus 2. Why? Well, because we only had beta 0 and beta 1. That was our value of p. We decide to don't reject the usual way, and then we state our conclusions. One additional note that I want to make about the conclusions that's not listed here is that you also need to emphasize the following. Given the other predictor variables remain in the model. So the same kind of conclusion that you would have in Chapter 2. So if you reject HO, that's, or let's say if you don't reject HO, then you say, well, there's not sufficient evidence to indicate that X and K is important to include in the model. But now you have to include the additional part here, given the other predictor variables are in the model. Because obviously, if X and K disappears, you still do have the other predictor variables. What you'll see in project number 3, in particular, for the acetic acid variable, that if you remember in the very first project, we found that acetic acid variable to be important. We rejected HO for the t-test. But now, once we include the other predictor variables in the model, we end up not rejecting HO. So that's why adding some additional stuff like this is important to put. We'll talk more about the project number 3 later in that aspect that happens. Okay. Well, what about a p-value? Now, obviously, when we're using a computer, using a p-value is often a little bit quicker because we don't have to actually find the critical values ourselves. So think about that when you're doing a test. Of course, you want to be as quick as possible. So what will be the p-value here? How would I calculate a p-value? Symbolically. You don't know, you just rely on the computer to do it for you. This might be a good test question. Note that I wrote it with my electronic pen, so probably didn't work very well on my piece of paper.
It's a probability of T minus T squared.
I'm sorry, probability what?
Value of T minus T squared greater than alpha.
There's your p-value. Hopefully that looks familiar. 2 times the probability, random variable A, when it has a t-distribution with the correct degrees of freedom, is greater than the absolute value of t star. Just basically took that from Chapter 2 and took that from Stat 801. Then, in your critical value part, you would state alpha, and then how do you decide if you reject or not? Well, you look to see, is the p-value greater than alpha or less than alpha? Okay, let's take a look at an example. This is the NBA guard data set that was first introduced last time. Here's the sample regression model that we were dealing with. We had minutes per game, height, and free throw percentage in the model. And suppose we're interested in this. Is player height linearly related to PPM given MPG and free throw percentage are in the model? So what this is saying is this. Given that you do have these other 2 variables in the model, does, let's say, maybe PPM increase in a linear manner with height? Or does it decrease in a linear manner with height? As a basketball fan, I would expect, if there is an association here, I would expect it would increase. As height goes up, then you would expect the player maybe to be a better basketball player because simply they can see over other players and shoot the basketball more easily, perhaps. Let's use alpha 0.05 then to actually do this kind of hypothesis test. And here's some of our code and output. Just as a reminder from last time, when we actually use the LM function, we have our response variable ppm, and then we say tilde, and we separate our predictor variables simply by plus signs. I summarize the information that LM gives me. I put that summary information as sum.fit just so that I can give you a more, or give you less output, so that then when I say sum.fit $coefficients, I get a table that would normally be in the summary mod.fit output. Okay, so let's focus on height. Here is B2, or you could say equivalently, because sometimes this is more descriptive, B sub height. Here is the square root of the estimated variance of B2. Here's my corresponding T star, and then the corresponding p-value. These are all located in the same places that we would expect from what we saw in Chapter 2. So let's go ahead and do the test then. State my hypotheses. Beta for height is equal to 0 or not equal to 0. Find my test statistic. So again, all I did was, here's my 0.036. Here's what goes in the denominator, 0.0015. I hypothesize it to be 0, and I get 2.42. Critical value, I could, if I were to do the test like this, notice a little omission here in the notes. I could just simply go to R, get my QT function, get the critical value out to be plus or minus 1.98. Test statistic is greater than the upper critical value, so I reject HO. And what does this mean? Well, there is sufficient evidence to prove that height is linearly related to PM, even after you take into account minutes per game and free throw percentage. Any questions? Well, let's look at other portions of this output here. Notice for minutes per game, we have a p-value that's quite small, so indicating there is sufficient evidence to indicate minute per game is important, given height and free throw percentage on the model. Well, let's take a look at free throw percentage, 0.64. So there's not sufficient evidence to indicate that free throw percentage is important, given the other variables in the model. But of course, you got to be careful, and we discussed this some in Chapter 2. You got to be careful with what this don't reject HO means. It does not mean that free throw percentage has been proven to be not worthwhile to have in your model. It does not mean that. It does not mean that free throw percentage has no effect at all on PPM. Why? Two possible reasons. A type 2 error could have been committed. Someone tell me what a type 2 error is?
Don't reject the show.
Yeah. So, from set 801, the probability that you don't reject HO, given HA is true. In a hypothesis test, we do not control the probability of making that kind of error. What are we stating? Alpha. That's the probability of a type 1 error. That's what we're controlling. We're not controlling the probability of a type 2 error. Well, it's unlikely. What happens if the probability of a type 2 error here was 1?
Never reject.
Well, that would cause us some problems. At any time that we say don't reject HO, actually HA is true. Okay. Another reason is because of this. Maybe a more complex relationship exists. So far in this class, we really have focused on some simple relationships here, typically a linear relationship. But you can imagine perhaps a situation where maybe free throw percentage square wasn't needed in the model. Now let me draw a plot here to help emphasize this. So let's put free throw percentage here. And on the y-axis, I'm not going to put PPM exactly. I'm going to put an adjusted version of PPM. And we'll learn more about how to do this in Chapter 7. let's say adjusted ppm for the effects of minutes per game and free throw percentage. So you can think of a response variable that, let's say, now takes out the effects of these other two predictor variables. Now if, and then I did a scatter plot. If I had something that looked like that, then for a linear relationship, if I were to actually simply fit a model for this adjusted ppm with free throw percentage itself, the model will look something like that if I were to draw it. And as you might expect, then if you were to do a t-test, you're going to conclude don't reject HO. But however, there's still a relationship there. We see it. In fact, it's a quadratic relationship. And if this was true, something like this could happen. So, you just have to be careful with what actually don't reject HO means. Lastly here, we could also do a Bonferroni adjustment. Remember from chapter 4, what we just did here was 3 different hypothesis tests. Each of them have a particular type 1 error rate. And the overall chances of making at least one type 1 error increases for every single test that you do. So to help control that, you could use a Bonferroni correction if you wanted to. So in this case, we could say, let's compare our p-values to not 0.05, but how about 0.05 divided by 3? Okay, page 637. So back in chapter 2, we looked at analysis of variance in the context of a regression model. And our ANOVA table is the same format as before. I've put in what the actual matrix formulations would be for all the sums of squares that we saw in chapter 5. Notice these differences, though, from chapter 5. Degrees of freedom, p minus 1. Before in chapter 5 and chapter 2, we had just a degrees of freedom of 1. Again, now that we have more than one predictor variable, that's why we see p minus 1, the number of predictor variables. Again, for mean square, we would take the sums of squares and divide it by the corresponding degrees of freedom. And we can form an F-test statistic to do some stuff. Take MSR divided by MSE. Here's what the F-test statistic tests. Remember, back in chapter 2, I said the F-test is going to give you exactly the same result as a t-test when you have one predictor variable. Now that we have more than one predictor variable, that no longer happens. Because what an F-test does, it kind of gives you an overall measure of your model. So a t-test looks at one variable at a time. An F-test here looks at all your predictor variables at exactly the same time. So what it tests then is this. HO beta 1 is equal to beta 2 is equal to beta sub p minus 1 is equal to 0. So notice what this means then. Your model is just very simply expected value of y is equal to beta 0. HA says at least one of the betas does not equal 0. 1, 2, 3, however, you don't know exactly how many, but at least one. This F star, if you think of it as a random variable, has a F distribution with p minus 1 numerator degrees of freedom and n minus p denominator degrees of freedom. Again, in chapter 2, this p minus 1 again was just 1. Now, since we have more than one predictor variable, now it's p minus 1. And we simply reject HO if F star is large, subject to the F distribution. Well, why do we do that? It goes back to the demonstration I gave you in chapter 2 for why we do that. So, let's take a look at an example. I'm going to do a split screen here too. So here's our ANOVA table. And with the NBA guard data set we're going to use here, you might remember from chapter 2 we looked at the ANOVA function. We're going to be using that ANOVA function a lot more because it has some nice uses to it now that we have more than one predictor variable. But here's our first use of it. If I say ANOVA mod.fit, and just so I can save some of the results, I'm going to put the put it into an object called ANOVA.fit for the lack of a better name, and then print off ANOVA.fit. And this is what we get for what R refers to as the ANOVA table. So we can see the last row there, residuals, corresponds to our error row in how we represent the ANOVA table based on how our book does. But these first three rows actually is this regression row broken up by predictor variable. So for example, if I were to add these three sums of squares together, I would get this SSR that's right there. Okay? Now, what this F value and this P value is representing, we'll talk about that in Chapter 7. It gets a little bit complicated, so I don't think it's worthwhile to talk about it here. But this is not exactly what's happening up here. Okay, so just stay tuned on that one. There's one other small thing I want to point out here, and that is, how could I get R just to tell me exactly what this SSR would be by actually having R sum it together? Let's talk about that. It's just more of a coding aspect that I want to mention. So I put the result in ANOVA.fit. So that means then I can say names ANOVA.fit to see what's inside that list of information. And notice what it ends up giving me is basically the columns for this particular kind of object. It gives me the column names of what we saw there. And notice there's a column called sum underscore SQ. I'm sorry, sum space SQ. Let me actually, I think it's going to be a little bit easier if I run some of this right here. Okay. Now, if I want to get then these sums of squares, what you might think is this. Let's just type ANOVA.fit $SUM space SQ. I get an error message. And the reason being is because of this space that's in there. What you can do instead, whenever something like this occurs, and this happens a few times in R, put a quote around it. And there, notice what I'm getting there. I'm getting all the sums of squares. Just a small syntax thing, but I do want to mention it. You could always use the quotes whenever you did the stuff after the $sign. Obviously, it's more convenient not to, and only use it when it's actually needed. So if I wanted to actually then sum up the first three sums of squares that are listed there, just do my bracket 1:3 to get the first three, and then use the sum function, and there's my SSR.
Isn't there somewhere in the output that you edit it automatically?
Maybe later. I'll mention it. I think we will have to actually use it. There's other ways to use the ANOVA function from how we did in Chapter 2 that allows you to get it. And I just wanted to relate what we were doing in Chapter 2. Okay. So let's continue then with this example. Since the ANOVA function, the way that we use it right here, doesn't actually give us our F test statistic value to perform one overall test to determine the importance of the predictive variables in the model. So let's look at how we can get the correct F statistic. It's actually not that difficult. This would be one way. So this is my model, and what we can do is simply look at the old summary mod.fit output to get the F test statistic. And here it is. Towards the bottom. So here is my F star, my numerator degrees of freedom, denominator degrees of freedom, and then p-value. my test. If you notice up above here, I've actually put the results from summary.fit into an object called sum.fit. Go to that portion of my output. If I do name sum.fit, we see there's a few things there that might be of interest to us. In particular, I guess for this specific situation, there's one called F statistic. And notice what that gives me is my F star in the corresponding degrees of freedom. Okay. So I can use the QF function then to get the critical value as you might expect. And also, if I wanted to, I can get the p-value from the PF function as well. So let's go ahead and do the test quickly. Step 1, state your hypotheses. So notice all the betas are equal to 0 in HO. Test statistic from the output is 7.26. Critical value is 2.69. Step 4 here, I decided to actually draw out what we're doing. So there's the F distribution. We see the actual critical value shown here. Again, that helps us determine what's a large F star to decide, yes, there is sufficient evidence to reject the null hypothesis. We notice that the test statistic falls way on the right-hand side of the distribution, so we say since 7.2 is greater than 2.7, reject HO, and thus the model is useful for estimating PPM. A little bit more quickly, we could have used the p-value and found the same thing. Now, I want to emphasize that how this result's not necessarily surprising to us for this particular model, because we had done the previous 3 t-tests for every single variable individually, and 2 of the 3 rejected HO. So if I'm doing an overall test here, you probably would expect that you would reject HO for the overall test, and in fact, that's what we do here. So one reason why I emphasize that is that this will help you prevent maybe mistakes later on. Because if you had the results disagree, where we wouldn't reject this F test, you might be thinking, wait a second, did I do something wrong here? Because the t-test actually did reject. So just a helpful check that you can do on your own when needed. Our authors will call this particular F-test that we just did here an F-test for regression relation. Other people, and I often do this myself, call this an overall F-test because we're looking overall at our model. Later in Chapter 7, we will look at what's called a partial F-test, which will allow you to test part of your model, as many variables as you want. And so that's why it's important to make the distinction from F-tests to overall F-tests. Anyway, so I'm sure all of you right now are probably wondering to yourselves, why do we need 2 different ways to basically assess our model here in terms of through these hypothesis tests? Why not just simply do all these t-tests individually? Is that what all of you were thinking? Well, those of you who are awake, I'm sure we're thinking that. So here's why. And it gets into what we were talking about in Chapter 4 when we were talking about Bonferroni corrections and stuff and why those are often needed. And let's consider a situation where you have 8 predictor variables. So that means 8 individual hypothesis tests would need to be done. And suppose we use alpha 0.1 for each test. The problem is determining what is actually the overall type 1 error rate. I mean, what's the probability you make at least one mistake? Assuming, let's say that, what's the probability you make at least one mistake? And what one could do is, it's a difficult thing to actually find what that probability is. So if we make some simplifying assumptions here, we could find a probability. Think of that maybe as an approximation. So if we assume independence amongst the tests and use the binomial distribution, the probability of making at least one error, given that HO is true on each of them, is 57%. That's not good, obviously. That's if you were to do the individual t-test. But instead, if you did one F-test at the same alpha level of 0.1, what's the probability of making one type 1 error? Well, 10%. That's why it's nice to have this overall F-test to get a general sense of what's occurring with your model. So then, well, how do you know which to use then? The F-test or T-test? Maybe we shouldn't use T-test at all. Well, yes, you should use T-test too. But this is a general recommendation then of how to proceed when evaluating the variables in your model and whether or not they are important to include. First of all, simply do a F-test, overall F-test. If you don't reject HO, then stop. There's not sufficient evidence to indicate that any of your variables are important. If, however, you ended up rejecting HO, okay, now figure out which variables are important. Go to this step 2, do individual t-tests. Yes?
If we fail the F-test, it is possible that one of the variables is sufficiently nonlinear to pull all the. We can't just not do individual tests.
Okay, let's back up a second here. Now, so you said if we don't reject HO, well, why don't you repeat what you say?
Basically, I'm saying that if we fail the F-test, it's still possible that several variables in the model that are not significant skew the result. We basically need to look at the model, simplify it, and then run the overall test again.
Not necessarily that would happen, because I mean, if there is actually
I'm
one.
not saying that it's necessary, but it can happen. But I'm saying we can't just say don't reject the HO and say.
If there was, so I think what you're saying is you're worried that if the other variables, let's say if they're not important, and you had one variable that was important, those other variables are going to skew the results. And that, generally speaking, would not happen. And you could actually do some simulations to show that. Perhaps that would be a good idea for the next project. No, seriously. That generally speaking would not happen. I don't want to say that it would not happen. Because I'm thinking of I'm thinking of examples in other contexts outside of this course.
When you have an interaction between the variables.
Okay, I think that's one of the things I think I was worried about when you first were saying this. What we are assuming then is that we have gotten the variables in their correct form. So if there is a quadratic term, it's in there when we're doing the tests involving the F-test. If there is an interaction, again, we'll see that in Chapter 8, if there is interaction, it's in there when we are doing this F-test. So that is the assumption that we have the variables in the correct form. Okay. Obviously, if you don't have the variables in the correct form, what you're saying, yes, indeed, could happen. Okay, so simply with the NBA guard data example, here's our model again. The F-test, the overall F-test rejected HO, and if we proceeded to the T-test, then we can see, of course, we had 2 reject HOs and 1 don't reject HO. Okay. That takes us then to page 643. Coefficient determination, otherwise often just simply referred to as R squared. We saw that first in Chapter 2. The idea simply extends here to multiple regression model 2, but just realize that when you're interpreting it, think of it in the context of now you're saying that all your P-1 predictor variables are explaining a certain amount of variability about Y. And so 100 times R% of the variation in Y can be explained by using the predictive variables to estimate Y. This is just a very standard interpretation Of course, when you phrase that kind of interpretation or project or test, replace what's underlined by what they actually mean, like what is what. A note that we saw back in Chapter 2 that I just want to remind you about, use R squared as a measure of fit when the sample size is substantially larger than the number of variables in the model. Otherwise, R squared could be artificially high. We saw that dramatic example where we had one predictive variable and we had only 2 observations. You always get an R squared of 1, no matter what. That's not good. But the second one's very important. This is something new. As more predictive variables are added to the model, R squared will always increase, even if the additional predictive variables do a poor job for estimating Y. So let's put this in the context of the high school and college GPA example that we've looked at. We saw high school GPA used in the model to predict college GPA had a large R squared. I think it was 0.8 something. Now remember the other predictive variable that we looked at, number of times you eat pizza, okay? And we saw when we just looked at a model of that with college GPA alone, there wasn't really any relationship. But if you were to add number of times you eat pizza to the model that has high school GPA in it already, your R squared is still going to go up, at least a little bit. So now why is that of concern? Well, the larger the R squared, the more variability that's being explained by your predictive variables. So you might think now the model that has then these 2 variables is better than just simply using the model that has only high school GPA in it. Well, that's not a good thing to have happen. So because of that, instead, there's something called the adjusted R squared, which prevents these, let's call them nonsense variables, like number of times you eat pizza, from making you think now that the model is better, including that variable in the model, when in fact it really doesn't have a relationship with the response. So this is what the adjusted R squared looks like. It's just a simple transformation of R squared itself. So 1 minus n minus 1 over n minus p times quantity 1 minus R squared. And we call this R squared A in a symbol form. The adjusted R squared cannot be forced to increase as R squared by adding these potentially nonsense variables. So because of that, it's better to use the adjusted R squared than just the regular old R squared. The interpretation of this adjusted R squared is just basically about the same as what we had for R squared. So you can use pretty much the same exact interpretation. Note that the adjusted R squared will always be less than or equal to the original R squared. And hopefully that makes sense in the context of how I introduced that in terms of nonsense variables added to your model is going to always increase R squared. Unfortunately, though, adjusted R squared at times can be a little bit less than 0. So, R squared was always between 0 and 1. But adjusted R squared can be just a little bit less than 0 at times. But those are extreme cases. What's that?
What's the interpretation?
Well, like I said, the interpretation is about the same. There, about. When's that going to happen? All your variables in your model are not helpful at all. Okay, so that questions then why you would even use the regression model, why you would even want to interpret an R squared or adjusted R squared. So let's look at it in terms of the NBA guard data example once again. So what we're going to do is look at 3 different models here and look at the R squares and adjusted R squares to see what happens. So the most basic model only has MPG in it. I'm going to put the results in an object called mob.fit1, summarize the fit, put that in sum.fit1. Then let's look at a model with both MPG and height in it. Remember the Ttest for MPG and height were both resulted in small p-values. And remember, we started off with the model that had all 3 variables in it, that included free throw percentage. So to have a nice little table then that summarizes everything, I'm simply going to create an object called r² values, put that in a data frame, have some nice labels to my models that I'm looking at. I'm going to pull out the r² and also the adjusted r² components of the sum.fit objects. Do a name sum.fit so you can see that indeed that those exist. And here's a table of my results. So with just MBG alone, the r² is 0.128, adjusted r² is 0.12. So, again, 12% of the variability. While it's a small amount, still 12% of the variability, or a little bit higher than 12% of the variability, is explained by minutes per game. If I add height to my model, notice my r² goes up, my adjusted r² goes up as well. And that should make intuitive sense that this would happen because, again, the t-test that we were seeing before showed that, yes, there was like a height effect. But now when I added free throw percentage, look what happens to r². It still goes up. But remember, with that t-test that we saw, given MPG and height were in the model, free throw percentage didn't have a significant effect. The r² still goes up, suggesting if I were to use r² alone, that was a better model. This explains more variability. But the adjusted r² goes down. So this process that we just did here finds that if I had to pick one of these models, the second model would be best. Now, one reason why I go through this little exercise here is because this is going to lead us up to what we're going to do in Chapter 9. Chapter 9 talks about situations where you have, let's say, a bunch of predictor variables, and you don't know which ones to include in your model. And we will discuss what are called model building techniques to help you build a model that uses the variables that are the best, that are actually having an effect on the response. And what I just showed you here was a very simple version of a model building technique using r² and adjusted r². Are there any questions? Okay, page 647. So let's say that you want to come up with a confidence interval for the expected value of y. How would you do that? Well, how about we put, for the corresponding x values, suppose we put them into a vector. So we have the usual, let's say, first element that's a 1, just like what we have in the X matrix. And then the second element is your variable value for x1, third value is variable value for x2, and so on. Then as what we saw in section 513 then, the estimated variance of y hat, which you would need for the confidence interval formula, is the mean square error times our vector transpose, times x prime x inverse, times the vector transpose. And just to put this into more of an intuitive framework, remember what our estimated covariance of B was. MSE times x prime x inverse. And essentially, that's what we see here. MSE, x prime x inverse. And this part here with the variable values allow you to grab out of x prime x inverse the stuff that you need in order to do the variance calculation, simply put. So I use this estimated variance then in our formula for our confidence interval, same as in Chapter 2 and Chapter 5, except now instead of having n minus 2 there, I have n minus p to reflect that I have more than potentially one predictor variable. You could also do prediction intervals as well. The same thing holds, except for now, of course, I have a 1 there instead. You could do Bonferroni corrections as well, or Bonferroni adjustments too. Let's look at an example. This involves Reggie Miller. Reggie Miller is another NBA great. I think he's in the Hall of Fame. Does anyone know if he's in the Hall of Fame? I think maybe just recently. What's that? Yeah, I would assume that he will be someday, even if he isn't in there right now. Maybe that should be an extra credit question on the test. Is Reggie Miller part of the Hall of Fame? Anyway, I saw some people write that down. Anyway, so this was, for this particular season, he played 36 minutes per game. He was 6'7", so 201 centimeters tall, and has 88% free throw percentage. Let's use then this model that we've been using before to estimate his PPM, and then also get a confidence interval for the expected value of PPM and a prediction interval for the expected value of PPM. So for Reggie Miller, his estimated PPM, plugging in those predicted variable values, 0.5156. This particular season, though, notice that his actual PPM was higher. We can translate this to minutes per game by taking PPM times the minutes per game he actually played. The estimated PPG, points per game, 18.57. His actual was 21.2. So you can see that he's doing higher than what would be predicted from the model. Let's find confidence intervals and prediction intervals then for someone, not necessarily him, but for someone who has these exact same predicted variable values. So let's take a look at this. First of all, what I want to do is get Reggie Miller's predicted variable values out of the data set itself. Remember, the data is stored in NBA. And I don't know if I've shown you this technique before, but here we have the NBA. Let's actually just take a look at the NBA guard data set again. So there's the first 6 observations. I just want to pull out Reggie Miller's. So if you notice, then if we looked at last names, we could have a good shot at getting just Reggie Miller's out. And if I do this, NBA $last.name equal Miller, what's R going to do? Exactly what's R going to do here. It's going to search for the name Miller. Basically what it's going to do is compare every single last name to Miller and return trues and falses. So there happened to be only one person that season with the last name of Miller, player number 62, in terms of everything's in alphabetical order in the data set. So I guess row number 62 matched Miller. Okay. Now, notice then, if I did NBA bracket 62, comma, end bracket, I get Reggie Miller. Alternatively, a little bit more general approach is this. NBA bracket, I put all those trues and falses then for the row numbers. Whenever there's a true, R is going to return me that particular row of the data set. So that's a convenient way to do it, especially if you are trying to pull stuff out of a data set that doesn't necessarily have only, let's say, one element, and you don't know where that element is. So that's a nice little technique of data management. So that's how I can get Reggie Miller's predicted variable values out. I put then an object called Miller, and then I use the predict functions we've done many times before. Object equal mod.fit, new data equal Miller. Sure, we'll get the standard error calculations, confidence interval, 95% interval, and here we go. 0.4673 is less than expected value of PPM, is less than 0.5639. So just to make sure you understand the interpretation of this interval, what this says is that with 95% confidence, I would expect players with this particular minutes per game, this particular height, this particular free throw percentage, I would expect all players with that set of predicted variable values to have an average points per game of between those two numbers. Let's look at our prediction interval. Exactly the same, except for I put prediction there. And so this is my interval. 0.2986 is less than ppm, is less than 0.7326. Again, what this means then is that for a particular player that has these particular predictor variable values, their ppm should be between 0.2986 to 0.7326 with 95% confidence. That's the difference between the two interpretations. Here's a table summarizing these calculations. And let's focus on this where I put everything into the points per game scale. So I simply took the lower bound and the upper bound of the intervals, take it times the minutes per game. So Reggie Miller, his particular points per game was 21.2. Notice it's outside of that confidence interval. What does that say about Reggie Miller? Not necessarily. I guess you can maybe kind of say outlier, but I'm actually looking for a little bit something else.
Above average.
Excuse me?
He's above average.
Above average. Yeah. So for someone with his minutes per game, his height, his free throw percentage, you would expect on average to have a points per game between here and here. But he's above that. And one of the things that Reggie Miller was noted for was the fact that he was good at scoring. And so, perhaps what the Hall of Fame should do, if he's not already in there, is that for all the players out there that are under consideration, do some analysis like this. And if their points per game is actually above the confidence interval, then that says something about their performance. I have to admit this is a little bit of an ad hoc approach, though. But I think the reason why I do this is because I know there's, not everyone, but a lot of you are probably basketball fans, and you can relate then to an NBA great. Now that when we do a statistical analysis here, we can see that they're extreme. They're better than what we would expect on average. But notice here that for Reggie Miller, his points per game is within the prediction interval. Again, what the prediction interval means for any player with these predictive variable values, we would expect them to be between here and here with 95% confidence. And indeed, he is. Are there any questions? Okay, page 651 then. Since I'm not 100% sure that I'm going to get through all these, the remaining set of notes here, why don't we take a quick jump to the project and discuss that. Sorry to be jumping around here. So again, with the project, we're looking at this cheese data, and we're looking at this particular model that has 3 predictor variables in it now. We've talked about A, we've talked about B, and we've talked about D already. Part C, perform an overall F-test. So just like what we did in class. It's not too difficult. Part E, use a T-test for acetic acid with the help of the output from summary.alm. So we did that too as well today. This rest of the stuff corresponds to Chapter 7, so I'm going to not talk about that right now. Part F, the tests for acetic acid, we can just think of it as the T-test, resulted in a large p-value. However, this type of test performed for just the model that had only acetic acid in it had a low p-value. Why does this occur? Any thoughts? Let me discuss this here. Any thoughts? What's the difference between what, let's say, what the overall F-test does. I'm sorry. Let me reset that. What's the difference between what a T-test does for the model that has the 3 predictor variables in it compared to the T-test that only for the model that only had 1 predictor variable in it? What's the difference? Well, I kind of just gave it to you. Well, the number of variables. So I'm not going to give you the whole answer here, but if I have these other variables in the model, something's happening, something's going on that's causing this p-value basically to change. Think about it on your own. Next, for the mean values of acetic acid, hydrogen sulfide, and lactic acid, the 3 predictor variables, estimate the value of taste. In other words, find y hat. And then find a 95% confidence interval for the mean response. Use the predict function to help you with the calculations. Compare that to when we were basically doing the same thing for the model that had only acetic acid. You're going to see the 2 confidence intervals are going to be different. Tell me why you think that happens. And look at specifically the bounds of the interval themselves. What will we prefer with confidence intervals? We prefer confidence intervals to be as narrow, or let's say as small in width as possible. Well, look at which model results in that aspect, and tell me why you think that happens. Part H relies on section 6.8, which we will talk about very shortly. And then finally, part I here. Because the T-test for acetic acid had a large p-value. Again, this is foreshadowing stuff that we're going to do in Chapter 9. The backward elimination model building procedure would remove this variable from the overall model. And you will be left with only a model that has, you'd be left with a model that has only 2 predictor variables. Why that's done, we'll talk about in Chapter 9. But this is the model that you will be left with. I want you to find the sample regression model, and then, similar to what we did last time, plot it in 3 dimensions. Okay? Are there any questions? Okay, let's move on then and get back to the notes on page 651. Oh, that's good. We will pause for a moment here. Okay. So this is the last part of Chapter 6. Just like what we did in Chapter 3 now, we will want to do various diagnostic procedures on our model to make sure that we have specified the model correctly, the assumptions behind the model are at least approximately being satisfied, and so on. And the reason why we want to do that is because if we have some violations of our, let's say, our assumptions, then any kind of inference that we try to do, confidence intervals, prediction intervals, hypothesis tests that we do, we may get incorrect results. Again, what I mean by incorrect results, when I say I have a 95% confidence interval, maybe it's not truly 95% because some of the assumptions of our model have been violated. Okay, so we will want to do a lot of the stuff that we did in Chapter 3 to examine our model more closely. So, for example, we will want to do this linearity of the regression function check. Before, what we did was we took the residual, plotted versus the 1 predictor variable. I cannot talk now. Take the residual, plotted versus the predictor variable. Now, since we have more than 1 predictor variable, we're going to have more than 1 plot. We're still going to take the residuals, but now versus each of the predictor variables. The plot of the residual versus y hat. You'll remember we used that to examine non-constant variance. that plot no longer will look the same as what we had when we had residual versus the predictor variable. Because again, we have more than one predictor variable. This is the second time overall that we're going to look at diagnostic and remedial measures with a regression model. We will finalize how we actually do this in chapters 10 and 11. So we will have a third time coming up. To help you out, I have written a function for you, just like in chapter 3. This one's called examine.mod.multiple, and it's in my the corresponding file. Let me restate that. I have a function called examine.mod.multiple in the examine.mod.multiple.r file that will allow you to do a lot of these plots really simply. And again, the reason why I did that was long ago when I was first starting to do this class, I did have a function like that. Actually, I was using SAS at the time, and it just was one big mess to try to have the students do every single plot. So that's why I started doing this. Okay. Now, also, it's helpful in these situations where we have more than one predictor variable to do what's called a matrix of scatter plots, often called a scatter plot matrix, and to examine the relationships between the predictor variables and the response and the relationships between the predictor variables themselves. So simply put, let me bring up a window here, Windows Journal. This is what a scatter plot matrix looks like if you haven't seen one of them before. Let's say that we have a simple situation where we have y, x1, and x2. And then basically what we have is just a 3x3 grid of plots, where inside the grid we have plots, just simple scatter plots, y versus x1, y versus x2, x1 versus x2, and typically you won't have anything here, and then just kind of the reverse, x1 versus y, scatter plots. And that helps you, this is often one of these plots that are looked at the very beginning of your analysis to make a judgment on, well, does it look like I have some kind of relationships going on? So obviously you want to have relationships between y and x1 and y and x2 if you want x1 and x2 to be good predictor variables. But also you want to look at these plots here, your predictor variable scatter plots, let's say x1 versus x2 here, because you want to understand the relationships between your predictor variables too. Here's why. Let's say that there's a perfect positive relationship between x1 and x2. Do you need both x1 and x2 in your model? No. Because if you have x1 in the model, x2 is not going to give you any additional information about y, and vice versa. And in fact, if you did have both in your model, you can have some computation problems that pop up when you're actually trying to find your estimators, your B0, your B1, B2. We'll talk about that more in Chapter 7. So you want to actually avoid situations where you have predictor variables that are highly correlated, both in a positive and a negative way. You want to avoid those situations. And a plot like this gives you an initial examination to see if that's going to happen. Okay, so back to the MBA GUARD data set. Here's our model. Once again, MPG height and free throw percentage in it. Let me actually jump on over here to 10. Here's what my actual program looks like. Very similar to what we had in Chapter 3. To get the function into R, I can just simply source my code so I have access to the function. And then we go to my MBA example.R program to actually then run my function. It runs a similar way as before. Put in mod.fits. Well, do you want a constant variance test? Sure, why not? Do you want to do a box-Cox transformation, or at least find it? Sure, why not? So I put a true there. I put the results into save.it to save it. And let's actually print what's in save.it just to see what's going on. And here we go. So notice a whole bunch of plots have been produced. My mouse now has a plus sign there, meaning that I can click on the last plot to identify particular points. Notice semi-studentized residual versus y hat here. I have a value that's outside of my plus or minus 3 borderline. So I can simply identify that that is observation number 37. I can, what? Actually, no, it's not Jordan. I can stop to, let's say, move on to the next set of plots, and you see a whole bunch more stuff produced. So let's take some time to look at these plots so we can evaluate our model. So page 653, I'm actually going to go to Word to look at this stuff so I can draw on them. Page 653, we have our initial plots that just simply do box and dot plots of our variable values. That's it. Just to make sure that we don't have anything unusual going on. So this is a plot for Y. Here's a plot for MPG. This is for height. And this is for free throw percentage. And so, for example, we can look at, let's look at free throw percentage here. Notice there's actually some player that makes only about 40% of his free throws. I don't think Shaq was in basketball or in the NBA at the time, or was he? I want to say he wasn't. He was probably still at LSU, but so it's probably not Shaq there, but maybe I'm wrong. And what we're looking here, for example, is do we have values that are between 0 and 100? Because if you have something outside of that range, obviously you got a problem with your data. You have a data entry error. So that's one use that we can use for this. And so everything looks okay. On page 656 is where I start talking about certain aspects of going through and examining these plots. So you might look at the plots and also starting on page 656 simultaneously. So one of the first things that we want to do is to look at the linearity of the regression model. And what we do there is we look at these particular plots. Blow this up a little bit. So again, this is MPG, this is height, and this is free throw percentage. What we're looking for here is if we have just a random scattering of points, that means we have correctly specified the variable, the predictive variable, in our model. If, however, we see particular trends, like a linear trend, a quadratic trend, then that suggests to you maybe you need some kind of transformation of the predictor variable. Note that we don't use this plot to, let's say, determine non-constant variance. We don't look for additional parts, additional variability, or variability not being the same. And so what do you think of this residual versus MPG? It looks pretty randomly scattered, except for I'm just a little bit concerned that, we got some stuff going up here. And notice if I were to draw like a line here, you see a little bit of an upward trend. And perhaps this is maybe looking a little bit too much into this plot. But what one could do is draw a line through the plot like that, through the middle of the points. And maybe, you don't have to be definite right now, but maybe we need a minutes per game squared to consider in our model. Again, that might be pushing it a little bit, but that's based upon what I see on this plot. Residuals versus height. I don't really see any kind of specific trend there. You got to be careful with looking at the points over here because they're all by themselves. There's only 3 of them. Focus more on, do you see any kind of linear quadratic trend in there? I don't really see that. Residuals versus free throw percentage. Again, I don't really see any particular kind of trend like that. So what we basically said is that, well, maybe we want to consider minutes per game squared as a transformation. Maybe. Constant error variance. We will look at residuals versus y hat. What do you think? What are we looking for here? Changes in variability of the points. Now, when I look at that, I really don't see much. Now, you got to be careful over here because we only have a few points. So, that might be a little bit misleading. But, if you do look at that, the variability there is smaller than the variability there. Based upon this plot alone, I probably wouldn't be worried. I shouldn't say probably. I typically would not be worried. I guess I still qualified that one typically. The reason why I'm doing that is because, let's take a look at some of the output that we get that's inside save.it. Let's look at the BP test. What's the BP test telling us? Do we have problems with non-constant error variance? Yeah, small p-value. Levine's test. Now this is a little bit more difficult to do. Before we only saw one p-value because we had one predictor variable. Remember how Levine's test works. We, at first, break up our data into two parts based upon the median of the predictor variable. But now if I have more than one predictor variable, well, how do I break it up? So what you can do is, let's say for the first predictor variable, break it up by its median, and then perform the test like you would normally. Get a p-value of 0.057. So there's marginal evidence there of non-constant variance. For variable number 2, break it up by the median, p-value about 0.1. Again, marginal evidence. For the third variable, there's not really sufficient evidence. Of course, we could also do the Box-Cox transformation. For some reason, I failed to actually mention that on page 656, but you should look at the Box-Cox transformation as well. I get a lambda of 0.3, lambda hat of 0.31. Well, let's actually take a look at the corresponding plot. Actually, we'll go over here since we can blow it up a little bit bigger. So this is our corresponding plot. So what's that telling us? It looks like we might have some evidence because notice the confidence interval for lambda is kind of close to 1, but it doesn't actually contain 1. So maybe we could say marginal evidence. So of course, if lambda was equal to 1, that would say no transformations needed. So it looks like we want to explore this non-constant error variance issue further in our model, if we want to come up with a better, well, if we want to, we do want to come up with a better model. Okay? Uh, 657, we'll do 2 more. Outliers. Again, we would look at the plot of the semi-studentized residuals versus y-hats. And note that we do have one player that is outside this plus or minus 3 range. This player actually is a last name of Green. I want to say his first name was Seth, but I could be wrong. One interesting aspect of this particular player is that he only appeared in 13 games. If you're an NBA fan, you know that there's actually 82 games out there. So perhaps this is maybe leading that this one player who doesn't play that often is causing maybe some problems with our model. In fact, we will explore this further later in the semester, that players who are not playing a whole lot are potentially causing us some problems with our model. If you're an NBA fan, on your own, you can think about why that might happen. When do these players who don't play a lot, let's say who are far down on the bench, when do they get in the game? Garbage time. Okay. So they could be screwing up our model. maybe we should consider not including those kinds of players who are not, let's say, regular players. Maybe exclude them from our consideration for our model and thus narrow our population of inference to, not include them. More on that later. I'm getting a little bit too far in my head ahead of myself. More on that later. And lastly, I know we're out of time here. Here's a histogram of the semi-streetwise residuals and a QQ plot as well. It looks like we might have some deviation here on the right-hand side of the distribution. So we might want to consider, again, transformations. So why don't we just stop there? Are there any questions? Okay, that's it for today.